Good morning friends. In today's lecture we are going to see design of asynchronous sequential circuit. The given problem is design an asynchronous sequential circuit with two inputs x and y with the one output z. Whenever y is 1, the input x is transferred to z. When y is 0, the output does not change for any change in x. This is the given problem. This design problem they have given condition. So here let us assume x and y is the input and z is the output. They given two condition. If y equal to 1 means z equal to x. If y equal to 0 means z equal to previous state. This is the condition they are given in the problem. So from this condition we have to draw the state diagram. So let us assume 0 0 is the initial state. The output of the initial state is always 0. So this is x and y. Here this is the output. So for this state we have two possibility. Why two possibility? So this 0 0 can change 0 1 or 1 0. Why not it is 1 1? Because the 1 1 2-bit change 0 0 is changed to 1 1 means it is the 2-bit change which is not allowed in the asynchronous sequential circuit. So now we are coming to the problem. So the 1-bit change alone allowed for the asynchronous sequential circuit design. So the 0 0 can be changed to 0 1 or either 1 0. So now check what is y here 1. So now check the condition. If y equal to 1, the output will equal to x. So the output equal to x. What is x now? 0. Now check y. If it is 0, the previous state output is maintained here. Okay. Then coming to this state, here again there is two possibility of this state. This can be changed to either 1 1 or 0 0. Okay. Either 1 1 or 0 0. So if it is 1 1, 1 1 means the y is 1, so the output become x, so it is 1. Here 0 0 means the output is 0 because the y equal to 0, so the z is maintained as a previous state output. So this is already existing state, so let us stop here. So again this state is new state, so we will continue here. So this can become 0 1 or 1 0. So if y equal to 1 means output is equal to x. So this is 0 1 bar 0 is already existing state here. So we can leave this and we can come to the 1 0 state. So if it is 1 0, the output y is 0, then x is the previous state is maintained. So this is the new state because here in this state we got 1 0 divided by 0, but here 1 0 divided by 1. So this is new state. Again we are dividing this state to 2, that is 1 1 or 0 0. So y equal to 1 means 1 here, and here if y equal to 0 means the previous state output that is maintained here. So here this is the new state. So again there is a two possibility, either 0 1 or 1 0. So 1 means here 0 and 0 y equal to 0 means the previous state output is maintained. So check this. This is already available state, that is here, and here this state is already available here. So we are coming to this state. This state we have two possibility. One is 1 1 or else 0 0. If it is 1 1 means output is 1, already existing state. 0 means it is 0. Now we can stop this here. This is the design of asynchronous sequential circuit design. Now we have to name the states. So let us assume this state is A state and this state is B state and this new state is C state. You can ask me, ma'am, I can take this 10 state as a B and 01 state as a C. You can take it. Any state you can assign any variable. Then now coming to here, this is the new state. So I'm assuming this state is D and 000. This state is already available here. So this state is again A state. Then coming here, this state is D state and this state is A state. And here it is B state and here it is E state, new state, E state. Then here it is again D and 01, it is F state, new state, and this is already available state, that is B, and here it is C. Now let us see from the flow diagram how to draw the state diagram. So state diagram. So we are coming from the A state. So the initial state is A with 0 output. If I am giving 0, 1 input to the A state, it will go to the B state. So the state is in 0, 0 state. So if I am giving 0, 1 state to the A state, it will go to the B state. Output of the B state is 0, 1. So the state 0, 1 state is the B state. Next, if I am giving 1, 0 to the A state, then it will go to the C state with the output of 0, 1, 0. So this state is 1, 0. This is a self state. So this state is 1, 0 state is self state. If the present state and the next state of the input is same, means this is a stable state. So if I am applying 1, 0 to the state C, again and again it will retain the same state. So it is called stable state. So after that, if I am giving 0, 0 to the B state, what will happen? It will go to the A state. So 0, 0. So if I am giving B to 0, 0 state, it will again go to the A state. So if I am giving B to 1, 1, so it will go to the D state with the output of 1. So if I am giving 1, 0 to the D state, 1, 0 to the D state, it will go to the E state with output of 1. So this self state is 1, 1 and this self state is 1, 0. So if I am giving 0, 1 to the D state, so 0, 1 கொடுத்தேன் அப்படினா, it will go to the B state, 0, 1. So if I am giving 0, 0 to the E state, 0, 0 if I am giving to the E state, it will go to the F state with the output of 1. If I am giving 1, 1 to the E state, it will go to the D state. So here the self state is 0, 0. Then if I am giving 0, 1 to the F state, it will go to the B state. If I am giving 0, 1 to the E state, it will go to the F state. If I am giving 1, 0 to the F state, it will go to the 1, 0 to the F state, it will go to the E state. Then coming here, C state. In the C state, if I'm giving 1 1, it will go to the D state. If I'm giving 0 0, it will go to the A state. So this is the state diagram of the asynchronous sequential circuit. So this is the flow diagram of a given problem, and this is the state diagram. This from the state diagram, the next step is we have to go for primitive flow table. So now I'll explain you how to draw this, how to fill up this primitive flow table from your state diagram. So we got the state from A to F, that is the present state. So you should write A to F state, that is the present state. And we got inputs X and Y. So two inputs. For the two inputs we got 4 possible outputs, that is 0 0 to 1 0. So the order is 0 0 0 1. It is not 1 0, but it is 1 1. Why? Because the 1 bit change is allowed in the asynchronous sequential circuit design. So instead of 1 0, we are writing 1 1. The same method is we are following for K-map. So 1 1, it is 1 0. So for this inputs, we want to fill up the present state. So if I am applying 0 0 input to the A state, so if I am applying 0 0 to the A state, where it will go? It will retain in the A state. And what is the output? The output is 0, that we have to fill up here. Okay. Then if I am applying 0 1 to the A state, if I am applying 0 1 to the A state, it will go to the B state. It will go to the B state. The output is 0. But for the stable state alone, we should write the output. For the other states, it is not needed. So if I am applying 0 1 to the A state, the next state is B state, and the output is not needed. That's why I am putting dash. So if I am applying 1 1, so if I am applying 1 1, that is not existed, because 0 0 to 1 1 state is 2 bit change, that is not allowed. So that is both dash dash. Again, if I am applying 1 0 state, 1 0 state means, if I am applying 1 0 state means it will go to the C state and output is 0, but the output is not needed and it becomes dash. So how to find out your stable state? Why I am rounding up this state means, if the present state as well as the next state is same means, both the states are same means, it is a stable state. For stable state alone, you can write down your output. For the remaining states, it is not needed. You can substitute -1 or X. Similarly, we have to write down for the B state. So for the B state, if I am applying 0 0 means, what will happen? If I am applying for the B state, if I am applying 0 0 means, it will go to the A states. That's what I have filled up there. Then if I am applying 0 1, 0 1 means it is on the same state. So B comma 0 I should write. If I am applying 1 0, 1 0 means 1 0 that does not exist. So hyphen hyphen. If I am applying 1 1, if I am applying 1 1 to the B state, it will go to the D state. The output is 1. So here D hyphen. If my present state and next states are same states, then it is a stable state. For the stable state alone, I have written, I have rounded up. Okay. Then my present next state is C state. So for the C state, check now. If I am applying 0 0 to the C state, what will happen? It will go to the A state. Okay. Then A comma hyphen. If I am applying 0 1 to this C state, what will happen? That status does not exist. So it is hyphen hyphen. For the C state, it is hyphen hyphen. So if I am applying 1 1 means, so if I am applying this C state with 1 1 means, it will go to the D state. Then if I am applying 1 0, it will retain on the same state, C state. So that C state is stable state, because here also next state is also C and here also it is C. So if present state and the next state is same means, then it is called stable state. Then we have to round it up. Okay, similarly we have to write down for D, E and F. So after the design of primitive flow table, our next step is Merger graph. So Merger graph is used to reduce the number of repeated states. So how to draw the Merger graph? I'll explain. So there are 6 states available in your primitive flow table. There are 6 states available from A state to F state. So in this Merger graph, you have to go for column wise variable allocation and row wise variable allocation. In the column wise variable allocation, so remove the first present state, that is A. You remove the first present state and write down all other present states, that is B to F. In the row wise, you remove the last state. You remove F, then up to E you can write down. So draw the graph like this. Now you have to compare first two row and column, that is A and B you have to compare. So while comparing in the primitive flow table, AA, so it is AA equal 0 hyphen. So the hyphen stands for either 0 or 1. So this 0 is equivalent to hyphen. So here BB, then it is hyphen 0, then it is hyphen D equal, then hyphen hyphen equal, and C hyphen equal hyphen hyphen. So all present state, all next state as well as the output is equal. So then the state is called fully computable state. So there is no difference in the next state. So we have to put a tick mark. So this tick mark means fully computable. Fully computable means the next state and the output are same. We can represent this fully computable in by means of the tick mark. Then we have to compare A with the C. A with the C you have to compare. You come for now A and C. Now you compare A equal A0 equal B hyphen equal hyphen hyphen equal, then hyphen D equal, then hyphen hyphen equal, CC equal and hyphen 0 equal. So A, C is equal states, so fully computable state. Again you have to put a tick mark. Now you compare A with D. Now compare A with D. So A hyphen 0 hyphen, then B equal hyphen hyphen, then hyphen D hyphen 1, then CE. These two states are different, that is CE. Then remaining outputs are equal. If output alone difference mean you put a cross mark. Otherwise it is the different next states you have to write down. So if you are comparing A and D, the different next states are C and E. You write down the states. Then you can compare A with E. A and E. So now you compare A with E, AF. So that is the different state, AF, 0 hyphen, then BB, then B hyphen equal, hyphen hyphen equal, then hyphen D equal, hyphen hyphen equal, CE. So what is the two different next states, CE and AF? That alone you have to write down in this column, AF and CE. Now you compare A and F. Compare A with F. If you are comparing A with F, two different state. If we got two different next statement, that is not a problem. But the output is different means, so you have to put a cross mark. 0, here it is 1. The outputs are different, so you have to put a cross mark. So similarly, we have to fill the entire table. So after filling up this table, now we want to check which states are, again we have to cross mark. So the available states are CE. Now you check C with E. That is not available. So there is a different state in CE. So now you check AF. Within this box there is a two different state, that is AF state and CE state. So A F, that is the not computable state. Then all AF state you can cancel. Wherever there is AF, that is not computable states, so you can cancel out all the AF states. So after cancelling the AF state, now you check CE. Because of AF it is cancelled already. So CE also not computable state. Now cancel out CE also all around. Now after cancelling, the table is looking like this. So we are coming to the next stage of Mager graph. So we have totally 6 states A, B, C, D, E, F. Now A is compatible with B. Now draw a line. If it is fully compatible, A to B, you have to draw a line. Then A is compatible with C. Now draw a line to A to C. Then A is compatible with, check, it is not compatible, it is not compatible, it is not compatible. Now coming to the B. B is compatible with C. So B to C, one line. Then B is compatible with D. B to D, one line. Then D is compatible with E, one line. Then D is compatible with F. D to F, one line. Then E is compatible with F. Now in this diagram, you take fully closed path. So here the closed path are A, B, C and E, F, D. This is one closed path. A, B is one closed path and E, F, D is one closed path. So I am assuming A, B is equal to S0 and D, E, F equal to S1. There are two closed loops. Okay. So after this, I am going to draw the reduced flow table. So once after assigning the states, through the Mager graph, we have assigned ABC as one state, that is S0 state, and DEF as another state, that is S1 state. So totally the 6 states, present states, we have converted to only 2 states, that is S0 and S1. Now we should go for the reduced flow table. So writing this reduced flow table, we must compare the primitive flow table. Now already we know that A, B, C are the same state, that is I represented by putting tick mark here. So now compare this A, B, C. Here 3 states are equal, A. So it is S0 here, because A, B, C equal to S0 comma, the output is 0. Because the present state and the next states are same state, it is a stable state. For the stable state, we have to round up the state as well as we have to write down the output. Okay. Then for 0, 1, now compare B hyphen. So B state. So it is as it is again S0 state. So S0 comma 0 here, the second state. Then 1 state. So now compare 1 state. It is D hyphen D. So it is S1 state, S1 comma hyphen. So here I have represent S1 comma hyphen. Now coming for 10 state, C hyphen C. So it is S0 state again. So S0 comma 0. Similarly, DEF you have to compare. If you are comparing DEF, F hyphen F1. So it is S1 state. So again I am representing S1 comma 1. Then it is S0, S1 comma S1. So from the primitive flow table, we have to go for the reduced flow table. In this reduced flow table, assign the values for S0 and S1. If S0 equal to 0, replace all S0 value with 0. If S1 equal to 1, replace all the S1 value by 1. So here 0. So next is transition table. In this transition table, we are assigning the value S0 equal to 0 and S1 equal to 1. So here it is 0, 0 comma 0. So here substituting. So substituting 0 comma 0. Then here it is S0. So 0, 0. You see here transition table after assigning the values of S0 and S1. Then for S1 it is 1 comma hyphen, then 0 comma 0. So if it is a stable state, that is present state, and next states are same state, stable state, you should mark it as by rounding up. Then S1 means 1. So 1 comma 1, because it is S1 comma 1. S1 equal to 1, so 1 comma 1, then s naught is 0 comma hyphen 1 comma 1 1 comma 1. So I have write down the transition table. So after transition table I should go for realization using K-map. So the realization is very simple. So we got inputs of present state. The present state is represented by f, the next state is represented by f plus, and output is z, and the input is xy. So what is the inputs for the K-map? The inputs for the K-map is present state as well as the input. So the present state is represented by f, then and the inputs are represented by xy. So this we have to fill up. So how many outputs are there? Next state as well as the output. So 2 K-map, 3 variable K-map we should draw. So now for the next state K-map, that is a 3 variable K-map, we are taking present state as well as xy as the input. Now fill up. So the next states are 0 state, 0 state, so 0 0, then 1 1, then 0, then 0 here, then 1 means here also 1, then the first bit is MSB bit is next state bit, comma this state is output. So 0 1 1, I am filling in 0 1 1. Okay, now group it, you can get your Boolean expression. Similarly for the output you have to fill up the second bit. 0 0 hyphen means x, so 0 0 x 0, then here 1 x 1 1, so here also 1 x 1 1. After filling up you can get z equal to f. So now draw the implementation logic diagram. This logic diagram will work for our given problem. Thank you.